Yeah, so the title is about grounding LLMs in execution. It's actually a bit of a lie. I'm going to mostly talk about like LLMs and transformers and a bit of that at the end. Yeah, so I'm going to talk about LLM 101, but a bit as an intro and saying some stuff that are obvious and things that actually I think we should look at and things we probably shouldn't look at. And then talking about a bit about like why I believe LLMs need grounding and how we can do it, and giving some 2 short examples in math theorem proving and in code generation. Okay, so we all know it's like the core of transformers and LLMs is actually, the core of LLMs is transformers. Transformers, the core of it is self-attention. So self-attention is just a softmax of Q queries, key transposed and V. I think there's a lot actually that matters in this, and cyclically the complexity of self-attention has been caught into question and saying, okay, this obviously is like n square in n the length of the sequence computational complexity. Lots of people have worked on working on like log n, n log n, sorry, or even linear, so n complexity replacement for the self-attention. I think, as far as I know, everything has failed because lots of stuff works on small benchmark and very little methods work on harder, like all around problems. And with LLMs, it started not to be a big issue again. We're going to see why. Yes. So with LLM, we kind of like said, okay, this is maybe less of a problem. I think it's going to become a problem again, that it's in n-squared. Okay, briefly, why does self-attention work so well? So basically the reason why you kind of eclipse completely RNN. In RNN, you always have to be able to have computed h of t minus 1 to be able to compute h of t. You have this kind of sequential dependencies to compute the hiddens. So computationally, so that's the third point in this bullet in here actually. Computationally, of course, you have a comb, so you don't use your very parallel machines that are GPUs or TPUs as effectively as with self-attention, where you can compute everything in parallel. So that's one thing. It's like we can actually just spend more compute more effectively in training. So that's one thing. The other thing is actually in RNN, you cannot know when you add k, token key, k in the sequence, what you will need to predict token n, which is much further. Whereas in self-attention, you can, right? So that's a very strong property of self-attention, is like at any point in time in your sequence, you can have access to everything before, and you don't need to compress any information about it, right? Whereas in an RNN, each step you need to compress the information. So now there is a resurgence of state space models, which are basically RNNs, except for a few of the most recent ones which are hybridizing to actually come back to something akin to self-attention, or effectively hybridizing with self-attention. And so most of the state space models, they have the same design flows as RNN, right? So if that's the first kind of thing I would like to say, is like if people are interested in working SSM because they are so cool and trendy today, like we should work on the ones that don't have the same flow as RNN. Like let's not go back there again. Okay, so LLMs are just like stacks of those transformer blocks, right? So we have some norm, the self-attention, some norm, and the FFN. The self-attention, as we see, is O of n squared and times m. So n being the length of the sequence, and m being the dimension of the hidden layers, right? And FFN is O of n squared times n. And so when you have like a model, like for instance, all the 70 billion parameter models, like Llama 70 billion, for instance, Chinchilla 70 billion before that, you have roughly 80 such blocks. And their dimension for m is, I don't even remember, I think it's like 8k. And in the FFN, actually, there is a factor in front of the m. So it kind of, the fact that we make those models so much bigger than the transformers we were using for a long time, actually, which were around 100 million or 300 million parameters. Kind of eclipse a bit the problem of the n squared, because now the n, when you want to have sequences in the few thousands of tokens, which is what most everybody uses this model with, is the computational cost of the self-attention is actually completely dwarfed by the cost of the FFN. But the trend nowadays is actually to have like small models, like 7 billion parameter or up to like I don't know, 20, 30 billion parameters. They are very potent and that can use very long sequences. And even the trend is to say, let's have smaller models that have access to a lot of knowledge to do retrieval on very long sequences. So this problem of the n square of the self-attention is going to come back, because now we are trying to kind of limit the computation we put in the model, but because we want to also leverage more tokens. So this O of n square, I think, is going to come back. So anybody who wants to work on having a better self-attention is, this is, I think, a strong topic. I need to note, though, that on the engineering side also, there has been a lot of effort to optimize the self-attention, only recently. And I would say it goes hand in hand that the engineering side has made a bunch of progress to compute self-attention better with algorithms like flash attention. That actually we could scale this self-attention on longer and longer sequences. And there's been a lot of engineering development and very well thought out, very detailed algorithms for implementing self-attention at scale on like sequences of million tokens. That has enabled kind of a renewal of interest for like very, very long sequences in transformers. So just as a reminder for this, it's more like for, I would say, a glossary, but when we pre-train at least those transformers, we pre-train them with what we call teacher forcing, right? So what it means is exactly that when we see a single sequence, like the cat sat on the mat with beginning of sequence and end of sequence, we actually use the whole sequence as if it was n different examples, and where we have all the prefix and we predict only one word at the time. So all the words are the ground truth, right? And you must see that this is not how we use models when we generate. When we generate, we don't have the ground truth, right? So if we generate with an LLM, we're going to have a prefix, and then it's going to have to generate but it's going to sample something. Maybe it's going to sample something different from and it's going to sample. You're going to have to sample something different depending on that. And if it was it needs to sample cat here, and it could sample dog. So in generation, it's not exactly the same setting as when we're doing this teacher forcing, this big. Most of the training we do on these transformers, and that's why we'll have some shenanigans when we do alignment actually. Well, this slide is twice. Okay, so just to give also a rough ideas of what we do when we go from just training big transformers to like the kind of stuff like ChatGPTs, Llamas, Gemini, this kind of LLMs you use most often. There are a bunch of steps in training those models. So of course, first we take the text and we tokenize it. So it's just we say we're going to have a fixed set of tokens that are going to be able to encode every possible text we're going to see ever, because you cannot have like a fixed vocabulary. You cannot have a finite vocabulary of words, right? So this is an example of the GPT-3 tokenizer. And then we're going to train or to pre-train actually on a massive amount of data. So this is numbers that are public from Llama 2 actually. So for a 70B model in Llama 2, back then we are training on 2,000 billion tokens, so 2 tera tokens of training set for the pre-training. And roughly this takes 4,000 GPUs for 21 days, right? You could see all of that in the paper. So that's where most of the knowledge gets acquired in the LLM. And even if we get back to here actually, I would say most of the knowledge, if we look at this representation of the attention, it's probably stored in the FFN, because that's where most of the weights are, right? As we see, you have M. So here the FFN is like basically M times 4M matrix, and then another 4M times M matrix, whereas self-attention only has a M by M matrix. in terms of weights to learn, roughly in big O. So you have much more of the weights that you can train in the FFN, so that's also where you store the knowledge. So most of the knowledge acquisition probably is there, because that's more where most of the data and most of the computation is, right? And the computation is also very important to learning. It's not just the amount of data you have, it's the number of times you kind of update the model, right? And then to get kind of something where you can chat with, you need to teach it to follow instructions. And for that, we do RLHF, instruction fine-tuning, this kind of stuff. And I made the areas to respective size here. And so for Llama 2, it's roughly 1 billion tokens. So you see it's like much less data. So you cannot really teach the model lots of new factoids there. You're really teaching it to turn from a machine that is trained to just compress text, so predicts the next token, what is the likelihood of the next token, to take turns of speech. So understand the end of a turn of speech and understand, okay, now it's my turn to answer. And I'm going to not continue this sentence as the most likely, but start another turn where it's the most likely answer. So we do that, and we also, when in this kind of data, it's data where you have prompts and answers, for instance. And there are various methods to do that the most effectively as possible. And this, in terms of compute, it's very little for it. For instance, for Llama 2, it corresponds to 512 GPUs for 1 day, right? So that's not where you don't hammer on the model as much in instruct fine-tuning or in LHF as in pre-tuning. So I want to say one thing about scaling laws, because I think I did that because I saw your talk, Julia. And I think it's like, there's been a big debate about, do we still need scaling laws? What are they? Is chinchilla wrong? It's kind of, and so I think there needs to be two things that are, to put this into context. One is like the chinchilla paper, what it said was chinchilla optimal. It was only considering training optimality, and it was very clear about that. And so if you look at Llama 3 8B, for instance, the chinchilla optimality in terms of tokens you need for training so tokens not in tokens for training the Llama 3 8B is roughly 200 billion tokens. Actually, it was trained on 15 tera tokens, right? So 75x more. So it is considered not chinchilla optimal. Is it bad? No, it's because what you consider when you do chinchilla optimality is for a given budget of compute, if I want to train the best model I can, it's like what is the size of the dataset, size of model, right? In this case, if you consider the inference compute, for instance, you could say, if you're going to have to serve this model and the inference cost is going to trump by a lot the training cost, it makes a lot of sense to actually overtrain compared to chinchilla optimality your model, because all of this additional training cost in compute, you're actually going to gain back by having a better model for a smaller scale in inference cost, right? So that's one thing. And the other thing where I really don't like people eating on the chinchilla paper, because I think it was seminal and did a big turn in the domain that was good, is that you have to put chinchilla in the context, right? So in the context of chinchilla paper, we were going for bigger models are better without thinking of the size of the data sets. Before chinchilla, so this figure is from chinchilla, right? So you had GPT-3 was a 175 billion parameter. We don't know how much data there was, but probably like something like 500 billion tokens or something. And then Palm was being trained on 500 billion parameters on like 700 billion tokens, right? And so what Chinchilla said is like, actually, just if we care about being training optimal, we are training too big models, and we should care about having more data. Okay, and the last thing I want to say about scaling laws and Chinchilla is that we very often in communications, in papers, and in scaling laws actually, we conflate tokens for unique tokens. And this is not exactly the same thing. And we also often conflate tokens and updates. And those models are trained with different batch sizes, and unique tokens are not the same thing as tokens. So whenever you look at a study of scaling laws, or you want to say something about scaling laws. I think you should be very careful about that. That brings a lot of nuances in scaling laws. Yeah, so this is from XKCD. I think scaling laws, the problem is like, look so nice and tidy once you do them, and then kind of bring a lot of reassurance that you can keep extrapolating if you fit really nicely your data points. But I think it's a bit of a node sniping tool. And I would say we should always take them with a bit of caution. Okay, so now this is basically LLF Redux. LHF Redux, so reinforcement learning with human feedback, which is a big kind of contribution of ChatGPT. Is to say, okay, now we have those LLMs they're big, they know how to really compress very well the training set, but we do need to align them with what humans want to do with them, which is like get answers, right? And one way to do that is actually quite data efficient, is to do LHF. The way it works is we have prompts. I mean, we have humans come up with prompts and ask something to the LLM, and the LLM is providing two different answers. And then, for instance, right? Or you can have two different LLMs providing two different answers. And then you have humans rating or picking which are the better answer. And you just collate that in a training set. And you can do a bunch of stuff with those human preference judgments. So the first basic thing you can do, which works actually very well, is just reduction sampling. Is you say you're going to train a reward model, and most often we just take the same as a LLM and we replace the logis head by something we just train for regressing the reward, right? Picking the best answer. You train a reward model on those preferences, and then you take your LLM again, and you just generate a bunch of answers. So for instance, with the same prompt, you are going to generate like 10 or 20 or more answers, and you're going to do reduction sampling with your reward model, saying the ones that don't pass a threshold in your reward, you're not going to use them, and the ones that do, you train on them. The contribution of LHF was also to say we can do that with PPO, which is instead of just doing reduction sampling, you can actually train the LLM directly with PPO instead of training it supervisedly on the rejections, which is a bit more data efficient. And then there was a big new paper after that, and like a flurry of papers after that. One was DPO, which said, okay, you don't actually need the reward model. You can just use differences between answer 1 and answer 2 that was picked to train the model with policy gradient style losses. So one thing you may notice though is if you want to generate this data and collect this data, you first need to align somewhat your model that is not just going to continue the prompt. So for that, most often what everybody does is like you have a very small set of supervised data, which is really chat format, and you first fine-tune first time your model on this, and then you do this kind of LHF procedure. So yeah, and so for DPO, well, I don't think I need to go into the details for that, but okay, for DPO, basically, you don't need a reward model. You have this preference data, and the name is well named, right? It's the direct preference optimization. So you optimize directly the likelihood of the answer that is preferred versus the other one. One thing that is interesting here is that we see pi theta and pi ref. So pi ref is a reference policy, so it's the one with which you generated the data. Pi theta is the one you're optimizing, so you see it's an importance sampling ratio, which comes up very often in reinforcement learning. And that is something that is quite important when you do this alignment with LLMs, is that here, collecting this data is actually quite expensive. You need to collect it by asking humans, do you prefer answer 1 or answer 2? And this data actually gets stale pretty quickly, because if you want to use it just as preference data, you need to be pretty close to the policy. So it means that pi theta here is to be not too far from pi ref, right? And so yeah, here's what I wanted to chat about, which I think are very interesting problems to study, is on policy of policy, right? So if you're training your neural net and just your LLM and just telling it, okay, for every single token you have supervision, so you are training it in a fully supervised manner. This is classical supervised learning problem. You can be completely off policy. You are going to give a lot of signal for every token. But when you do LLHF, you are doing something a bit different, right? You are using only the signal of a reward model, which is, in the limit, it's actually just 1 bit per prompt and answer. And so here you have very little signal to tune your model. And the only way you can significantly change the model for the better there is that the model doesn't have to explore too far from where it is already, right? So when it's going to generate an answer, there's going to be an infinity of possible answers for a prompt it can give. And you need to, so for a given version of the model, if you update it for a bunch of steps, for a given exact prompt, which is a bit long, you could expect for a given version that you will have the same answer if you have temperature 0 almost every time you try it, right? But if you change the model, you can have a completely different answer. And so the reward model and this kind of bit of information you get from the human annotators on the pairs, it kind of only goes as long as the model will not generate a completely different answer for a given prompt. So that's this kind of off-policy, on-policy, off-policy kind of shenanigans we have going on when we do LLHF. And I think here you can see it as if for instance, the ratio, here the importance ratio of pi theta over pi ref is very low. You're going to get very, very little signal in your update for this r hat theta. It's going to be very low if your ratio is if your policies are too far apart. So that is an interesting problem actually that I think we need to have much more understanding. On policy, off policiness, in general in RL it's been very well studied. But the problem with the LLMs is that the action space is virtually infinite, right? Because it's a tokens we generate and they're combinatorics. So now we need to find a way to quantify what are the effective degrees of liberty of this action space that if we enumerate the tokens and their combinatorics is infinite, so that we can actually quantify what is the on-policiness and off-policiness of language models. So that is really, I think, a very cool but completely open problem in my opinion. Okay, I'm going to talk about stuff I know a bit better now, so code generations. The code generation didn't wait for LLMs to be a hot topic in machine learning, actually. We had some pretty good even deep learning based code generation with DeepCoder and some other papers in 2015, 2016. And now there is actually a renewed interest. So Codex was one based on GPT-3 that was in Copilot. And since then, all the LLMs kind of do a bunch of tasks of code generation and measure on code generation benchmarks. So the most straightforward task we think of when we do code generation is code completion. But there are a bunch of other tasks that are interesting. So program synthesis, which is basically I give you input-outputs and tell me the code that would generate this. So I give you 1 million input-output, tell me the code that generates this. Is actually an interesting problem in kind of generalization. Linting, typing, finding bugs, generating tests, and translating programs. There's a bunch of different tasks that are not just continue this or prompt you in or natural language to code. So this is Code Llama that I worked on. Yes, we translated the slides to PDF. I knew that was well, basically it's just an example that it really works like ChatGPT once you have aligned it. You can prompt it, you can get answers that mix text and code. And you can execute this code. So just briefly about Code Llama, it was a Llama 2 code expert. So we just took Llama 2 and we trained it for more tokens on code. And we actually didn't even change the initial dataset, we changed only the distribution. And in this case, it's really about, there is this number of tokens versus number of unique tokens. It's more that we actually epoched on the code dataset that was in Llama 2. So we trained the smaller models for 500 billion additional tokens, and the big model for 1 tera token. And another thing we did, so that's the extended pre-training we did for code, where we oversampled the code. And then we did a version which is Python specific, but it's just we oversampled Python there. And mostly we also did some long context fine-tuning, which I think now everybody does. Back then, not a lot of models were supporting, but this is like almost a year old, so everybody does long context fine-tuning nowadays. Yeah, and at the very end, as you see, so what's interesting to see here is like we did extended pre-training for like 500 billion or 1 tera token. Then we use 20 billion tokens for long context fine-tuning. And then just at the very end, to give it instruct following capabilities, it's like 5 billion tokens, which actually was actually pretty big at the time. Now people are using more, and that's for following instructions to code. Well, here it was another video, but basically this is just showing that we made it. Well, actually, Fabian, who is the only, we made it also able to work with context before and after the cursor, which is if you take an LLM by default, it's just going to complete after the current prefix, right? And so instead we added special tokens, let's say, so the fill in the middle token or infilling tokens, where we can rewrite any kind of context before and after by saying this is the context before, and then this is the context after, and then you have a special token that says this was the context after. Then you have the context before, and then it's actually just a task of completion, left to right completion. But the model is able to learn that between these special tokens, this is what comes after, so what it's going to complete. It's a very well-known phenomena of transformers that you can train them, telling them like between tokens, you need to leverage this data differently. And this comes into the pre-training phase, actually. So one cool thing we did in CodeLlama is we generated the figures with CodeLlama. But one less cool thing is that actually, yeah, that's so the transitions don't work. But so I add in this slide the prompt we had to save for this. So I think that's like the bittersweet conclusion about doing this is like those generating these figures is something completely doable for models that are almost a year old, right? So models nowadays they're very good at doing that. But we had to actually write a pretty detailed prompt to get it to do what we wanted, right? To make this figure, but to say a lot of details. We didn't get it right the first time, so we had to modify a bit the prompt. And so, in the end, what I had if the transition was working, was like the full prompt, which takes roughly the full screen. And for me, the conclusion to that is that we still have to be. We still have to iterate and be so explicit with those models to get what we want. If you actually know very well your way around that properly, it's maybe not like a big gain to do it by prompting. But it works. That's the interesting part of it. Yeah. So then we actually, if you're not familiar with code generation, I wanted to show you how we actually evaluate those models, because it's actually very cool that we actually evaluate those models this way, but it's also sometimes like, don't get your hopes up, the examples are pretty simple. So for instance, this is one example in human eval. So in human eval, you're given the part where the function signature and the docstring of the function, and you have to predict the part that is highlighted in blue. I mean, you have to predict whatever part you want, but you have to predict something, and then we will run unit tests that test if your function is correctly implemented. And that's what you see by when you see results such as pass at something in CodeGen. Pass at 1 means you have one try, and we execute your code, and if it passes the test, it's going to count as 1, and if it doesn't, it's going to count as 0. And okay, and so, well, we can't read that much, but so on the right, you have these evaluations. So you have the pass at 1 for the major data sets. Back then, CodeLlama was very good. Now it's like an average to mediocre models, but we have much better models. We have like Llama 3, which is So great for its size, for instance. Okay, so this is pass@1 by model size. Also, when it came out, it was actually pretty highly scoring, except for GPT-4 was better, but GPT-4 was actually a much bigger model. So that is what it's showing. And yeah, so pass@1 is just like one very commonly used metric. It's what is very useful for you if you just use this model with like, okay, I'm prompting you. I'm prompting you once, and I want. Yeah, okay. I'm prompting you once, and I want one answer. But if we're actually building systems around those code-gen models, we may be interested in stuff like pass@100 or more even, right? So if all we care is that they're able to eventually come with a solution, and we have ways to say if they solve the problem or not, pass@100 is basically computing, okay, if I give you 100 try to solve this problem, can you give me one correct solution, right? Okay, and so that's, for instance, what you have on the right is like, there's a bunch of research on how do we, so sample budget, right, on the x-axis, is number of tries you have. And if you structure the space of how you want to try, or how you want to use this sample, right? If you have a pass@100, how you want to use those 100 samples to figure out what to do, you can get pretty high efficiency actually, right? So here it's a paper that's called Parcels that compares AlphaCode and Codex. So AlphaCode is like was a model from DeepMind that is good at like specialized in like solving programming contests, but it does it in kind of a brute force way. Like it generates a lot of solutions as kind of a heuristic to pick the best ones and submit this one to the judge. But in Parcel, it's more of a iterative kind of an iterative refinement. It generates a few solutions and decides which ones it needs to generate after that based on other first inputs. And then you can have much higher efficiency than just brute forcing the space, right? And on the left, you have also, so this is also using execution feedback, but only at test time. So this paper that is a bit dated, right? It's March 2023, so ages ago in LLM, but it just took GPT-4 and said, okay, on a given problem, so this is human eval scores, right? You're going to try it, and as long as you don't solve this problem, but the test come back negative, but you have an execution feedback, it tells you, okay, error, syntax error, or this test doesn't pass. I'm going to add that to your context, and you go try again until you reach a fixed point or you start looping, and you get an improvement of more than 20 points when you do this kind of stuff. So both of those, they leverage this kind of execution feedback to be much more sample efficient, or to solve more problems than you can if you don't.
Sorry, this is during inference or during training?
Yeah, only during inference, most of those. And now I'm going to talk about during training. Yeah. So remember this LHF thing on the left. So what we're working on nowadays is what we call EF, where the E stands for execution. So instead of doing LHF, we only propose 2 or 3 alternatives to the humans because they cannot spend all their time reading answers. They cannot compare. A human cannot compare also like 1,000 different solutions. But what we can do, if we don't have to use a human for rating, we can generate like a lot of solutions. So let's say you have a prompt, you generate 1,000 solutions, you execute them, and then you have some feedback. Either you have like some seg fault, some crash, some syntax error, some tests that don't pass, and you use everything you have in your feedback to kind of score your solutions and to fine-tune further the model on the ones that actually do pass, or you can even train a reward model to say this is better than this other thing. Once you have things that are correct, you can train a reward model on being faster on profiling. So this is what we call RLEF, and you can do that to do post-training, or fine-tuning of the model so that it's aware of the execution. What is very different compared to when we just pre-train those models is it's actually grounding the LLM in how its generation is gonna be used, right? So when we have an LLM generating tokens, it's just generating token according to the most likely distribution, but there is no correlation. I mean, the correlation with how they get executed is very, very indirect. In pre-training, it's what's there ecologically in the data, because actually, probably if the humans wrote the code, they executed it. When we do RLHF, it's there because it's what humans prefer, and probably they prefer something which is more likely to work. But when you actually do RLEF, it's like the hard signal you're going to get from these tokens is that you executed them, and you want to train the model on that. And it can open a bunch of ways to train those models, which is to say, okay, maybe we don't want to just train the model to predict the most likely tokens or the best tokens. We also want to train the models to predict what is going to happen when we execute the tokens we generate. So why do that? You can do a lot of stuff with it. The first and most straightforward thing is, I was telling you about pass at 100 before. So if you're able to, if your model has, I don't know, a pass at 1 of 60 and a pass at 100 of 95, which for instance was the case of CodeLlama a year ago, you can say, well, if I give it 100 try, it's going to solve the 95% of the problems, right? So maybe if I just train it like that, not on the test, of course, but on the train set where it does have this execution feedback, it can learn to re-rank higher the solutions, right? Because when you have pass at 1, you could see it as like the highest ranked solution it could do is this one, but like numbers 2, 3, 4, 5 actually is more likely to solve the problem. So that's the first use, I think, of RLEF is not to teach the model new tricks, it's just so that the model ranks better solutions it can actually exhibit already. And then beyond that, it's to learn to solve problems you couldn't solve before. And that is much more hard, and that's where I think there's a lot of open problems. So if you had a pass at 1 million, which is 5%, it's very unlikely that by just doing RLEF without doing anything fancy, you're going to get your pass at 1 million to improve. And that's where there is a lot of research in how do we use the LLMs to structure the exploration in the space of programs so that we can find a self-implemented operator, right? And finally, other reasons to use that is simply to ground the world model, so that the model is more likely to understand what is kind of the acceptable range of input and outputs for programs it generates, or actually where a solution fits better than another. So how we are doing that? We need to generate massive amount of diverse code, and that is a big issue, even for re-ranking, because if you try and do pass at 100, and out of you 100 solutions, you have only 2 or 3 different solutions, the rest is just syntax difference. You're spending a lot of compute and not a lot of exploration for what the model should learn. We need to execute it at scale, which in the case of simple Python functions is easy, but in the case of more complex code with a lot of dependencies or with calls to other programs, it's actually quite hard. We need to update the model, which actually is not the hardest part, and repeat. Okay, this part I don't. Okay, so this. So these are some results on programming challenges. So apps is well, not just programming challenges. Apps is a data set with different sets of kind of programming questions. Apps introductory is more like CS 101 types of questions. Apps interview is actually programming interviews questions, and apps competition is actually programming challenges like ACM, ICPC, and stuff like that. And so what we see here is the baseline is so the baseline is the bottom line is a CodeLlama 7 billion base model. The orange line is when we actually fine-tune. So there is a train set that follows this format. When we fine-tune the model on this train set, just to learn to understand the way we prompt these models in these challenges and the kind of solutions that are expected. And then the line on top of that is when you actually, on the train set, do this kind of, okay, we're going to do 100 generations, and we're going to train the model exactly the same way as we do LLHF, but with this feedback. So you get this boost, this improvement over the already fine-tuned and converged solution. But there are some issues when you want to do it on harder problems and at a bigger scale. So those are the training curves, for instance. When we try to do many iterations of such a procedure, and what we found is when you do a bunch of iterated versions of this. So, for instance, here, like the x-axis is the number of times we actually update the model this way successively. You can, if you don't pay a lot of attention of modifying the model in different ways or in specific ways, or if you don't pay attention to the diversity of the solutions it's going to produce, you can actually break your model, and it starts to generate more and more of the same solutions. So here, what we see when we have the curve go down in terms of reward and pass at over time of training, what happens is, if we look into it, is the model is first of all, for the pass at 100, for instance, going to generate 60 different unique solutions once you have canonicized and like the syntax is exactly the same, and then you update the model maybe 10 times, and then it's after some time it's probably going to produce only like 20 or 15 different solutions, to the point that at the end of doing this process you're going to have only one type of solution per problem. This is very problematic because we actually do train on a different set than the test set. So what it means is that it's going to get more and more of the test set solution wrong, because it prefers effectively just a few types of ways to solve those problems. And another open problem in RLEF is basically how to beat the bitter lesson, which is just, okay, let's put more compute in parallel scaling. And so this is when you say, okay, we don't care. So this is a bit closer to what, for instance, AlphaCode or AlphaCode 2 do, which is just to say we don't care that much about iterated performance and improving the model small step by small steps. We just care about sampling a lot from a model, which can sample very diverse programs, and then rerun them. And what we found is actually if we sample 100 million samples for these problems, like the overall pass at score we get are still better than if we were putting the same budget in iterated sampling for RLEF. So if you just care about what are the amount of a problem I can solve for a given fixed computational budget, is still not it right now. Okay. Yes. Oh, I have plenty of time. So I'm almost done. I'm going to talk a bit about temperature scale large language model for lean proofstep prediction, which is how we also can use execution feedback for lean proving. And in this case, it's actually basically taking a code lemma and fine-tuning it on lean proofs and seeing how we can improve proofs. So it is actually a bit the same kind of base hypothesis, which is to say, okay, we want to big a bit log scaling of just putting more sampling budget, which on the left is for AlphaCode, but in the case of theorem proving. And so this workshop paper is basically about how can we find ways to generate more and more diverse proof steps, diverse examples for eventually doing this execution feedback with Lean. So you see, as we so on the x-axis for the theorem proving part is the timeout, which means basically the benchmark for Lean proof step performance measuring is to say we give you a time budget. You can do whatever you want in this time budget, but you are measured on the number of the pass at you have for this time budget. It's not a sample budget, because this way you can make the choice of having either a smaller model that you can sample more in the same time, or a bigger model, which is going to be more accurate, but that you can sample less. And querying, and in this time budget, you have the time that you have to run lean also. So this is an example of what it means to solve a proof in lean. The first step is like what we want to prove, which is quite obvious to prove, but still you say, well, you want to prove that a plus b plus 2 times c equals a plus b plus c plus c. And you do this by rewriting successive multiplication, one multiplication, rewriting add associativity, and twice, right? And so those are all the steps that are going to be executed. And at the end, you reach a proof because you have no goal, and you prove this, right? So this is the kind of stuff we want the LLM to generate, so that it guides. So we want it to generate the tactic for generating this. And yeah, so okay, so this is like basically a bunch of hyperparameters. But so in this paper, what we kind of showed is it doesn't. Well, so the previous state of the art was to use a reprover, right? Which so the passat one at 600 sequence was like a 5047. So it was a much smaller model. And instead, what we did there, well, what Fabian did there, was to fine-tune CodeLlama on those proof steps to guide the search procedure. And most of the work was in figuring out how can we, by exploring the parameter space of the temperature for sampling from the model and the models we would use, so either a 1.5 billion parameter model or 7B or 13B, what was the best trade-off, right? And actually, it was not a given, because in code generation, we actually also looked at, for instance, if you compare to programming contests, so for instance, AlphaCode, which has also a 1 billion parameter model and a 9 billion parameter model, for instance. For a given sampling budget in compute, what is the best model is not clear. And actually, in our case, sampling from the 7 billion parameter model or from the 70B model was roughly equivalent, right? Because we would get much better program generations with the 70B than the 7B, but it would cost more, and it was roughly zeroing out, right? Well, in this case, what we found is that for the complexity of the proofs, so it's under a bunch of assumptions, basically, this experiment, right? It's for this data set, Lean Dojo with 600 seconds timeout, or with 1.2k second timeout. In these cases, like the best model was 7B, which means you don't necessarily like either the proofs are not hard enough, or you don't necessarily need like the added complexity added capacity you get from a bigger model. Right?
Can I add something? You
Yes.
said something about learning the tactic for
Yes.
the proof. How does that happen? Is there a list of possible moves and then you just look at all of them, or?
Yes. So basically, you take a CodeLlama and you fine-tune. So there is a bunch of it's MATLib, right? So there is a bunch of lean that is that you can train on, which is MATLib, which is a bunch of proofs that already exist. That basically lean developers use to test new tactics. They know they have all the steps. They can, so you can train on that, right? You fine-tune your CodeLlama on that, and well, your models, and if you fine-tune it on that, is just good at looking at for a given problem. It's going to you prompt it, and it's going to give you some possible tactics. So what it's going to give you is basically a distribution. It's a bit like a policy, right? It's going to give you a distribution over which tactics you should try. And then for a given budget, you can say, okay, give me a bunch of different tactics I'm going to try with Lean. It's basically going to order you in which order you should try this set of tactics, right? It's going to give you a bias for the search that you're necessarily going to do with Lean. If you don't use a model there, you could very much still solve the same problem, but you would do tree search or heuristic guided search or exhaustive search for the tactics you want to use for solving this proof. So this is just like training those models, just a way to find a way to light with your small flashlight this huge search space of the tactics you want to solve. And so mostly like what we did there is to say, okay, what matters when we generate these tactics? The temperature matters a lot, and also for a given sampling budget, should we rather use like small models and generate more stuff, or big models and generate more accurate stuff? Right? Yeah, and so those are well the kind of data from the tables before put in different blobs. So this is what it looks like, right? So it kind of like on the left, it looks very messy. It kind of evens out a bit. That the model size is actually maybe 7B is a sweet spot, but it's not clear, right? It's a bit better for 1.2K seconds. It's a bit better for 600. And so those are you have different axes. So you have the pass-at rate, you have the number of search nodes, and you have the tactic success, right? So this shows that with the bigger model, the 13 billion parameter model, you still have a higher tactic success, so it's still a better model. So the problem is not that the 13B is worse than the 7B, is that it's not better than the 7B by as much to compensate for the additional computational cost, right? So I mean, this again, I have to say that this is very specific to this data, right? Maybe if the proofs that it has to do were one order of magnitude harder, maybe there are some cases then only the 13B model can be helpful for the search or more helpful than the 7B, right? But in this context, for a given budget, you don't need the bigger is not necessarily better. And on the right, you have if you expand that for a bunch of timeouts also, how does it play out? Because the setting for this benchmark is 600 and 1.2K, but it's interesting to see how does this evolve if we actually give it more and more computational budget. And in this case, actually, for even up to 1.2K, the 1.5B model is better, but eventually you have a crossover and the 7B is better. So it's what I think what we can see there, and I don't know if we did the study, but it's probably that eventually you will have used all the diversity of the tactics that you can generate. If you have an infinite sampling budget, right? Of course, the 13B should be better than 7B, which is better than the 1.5. Well, you can see a bit of that in like adding more and more time on time. Oh, well, that's it. I'm done. So do we have any questions?
I have a question. When you do LLEF, do your model always only learn like working code, or sometimes if there is missed error, you still feed that to give the network some like pattern tuning?
Yeah, it's a good question. So the results are presented. The only signal we were using is does it pass all the tests or not?
Okay.
So we have a bunch of different signals, like what is the type of error, can be fast, but right now it was just that. So that's
on the second question is like for if you have so many solutions, do you rank the solution? For example, do you rank the solution by how much memory it used or how much time it completes?
Yeah. So not in the result. In the results I show you, it was really well. The plots I showed you, I think it was we were generating 20 or 30 solutions for each problem, and then all the ones that were passing we would use as a positive feedback. But then, of course, if you have a bunch that pass and you have some that are 10x longer, you may want to downwrite that. If you have some that are 10x slower,
or the memory, it uses so much memory to serve it.
Yeah.
So I was intrigued. You had an example where execution for you is part of the fine tuning at the end, or
yes.
But then you had this thing where you kind of did this in context, if I understood correctly. Where when it failed, you gave it to him again and said, and here you failed, try again. So that yes. I view it like an RLEF, but in context, like chain of thought EF, so to speak.
Okay, so I think your question is two things. Is like one is, so this is reflection, yeah? This is not from so us, but this
is when you...
Reflection is only at inference time, but you can do it at training time too. Yeah.
Right, no, but isn't it a better route to do it always at inference time? Isn't it? I mean, I understand now inference is expensive, but on the other hand, for people who can't.
Well, no, I think it's not. It's just a low-hanging fruit to do it at inference time, but it should also be done at training time, because actually, you want, so whenever you use a model at inference time, you want it to be in distribution. So if you never trained it to fix its own errors, it's going to be somewhat out of distribution. Whereas if you trained it to fix its own errors and really giving it positive reward signal of having seen a prompt, having made an error, and then having fixed based on the execution feedback it got when it get it wrong, then it can learn to leverage this data to fix the error. If you don't train it this way, it's going to be a bit kind of by chance that it's going to maybe use this data, or maybe not use this data, but use a new chance to try at this problem to solve it the second time around, right? So yes, it's a longer fruit to use it only at inference time, but I strongly believe we need to find good ways to train the model to fix its own errors, and that it is in distribution to make errors sometimes at inference time.
It's a very last question, but for the residual apps, do you know why it doesn't improve that much on the left?
Yeah, because my hunch is that because problems there are quite easy actually, and
they already are solved by the fine-tuning.
Well, yeah, if you look at the passat rate, it's much higher.
Yeah.
And apps is a good data set in one way because you have this kind of gamut of difficulty, but it's not as good a data set because it's not as high quality as the other data set I was showing before. So I'm not sure the solve rate I'm not sure you can get 99 on everything, right? Yes?
If you need to have some feedback from external system at the training time, does this create problems for communication and not fully using the GPU?
Yeah, it's a great question. Actually, like basically the systems and engineering aspect of scaling this is a big part, because just from what you're saying, right? So if you need to wait some time to get the execution feedback, anyway, you never want to wait to update your model. If you have data to update your model, you want to update your model, right? So you're going to end up with like a producer queue and a consumer queue, and the consumer is going to be training the models on whatever data you have now and keeping the GPUs hot and training the model. So what it means is like if actually getting the execution feedback or generating, if you want to generate a program that is like a million line of code, or something like that, and then you want the execution feedback, just generation and execution is going to take a lot of time. And by the time you get the execution signal, you're going to have this off policy issue, right? Like your model here is going to have done like 300 updates compared to the policy that was generating this. So there's a bunch of ways to solve that. You can say, in the middle of the generation, we can change the policy. So that can alleviate a bit of the off-policiness issue for the generation. But if what takes time is to actually execute the program, if the program has to train a full neural net for a few days, this is an extreme case, right? But if the program has to do some requests that take some time and some computation that takes some time, there is very little way to kind of bridge off policiness, and then you need to be a bit more fancy in your algorithm or the way you use this data. Yeah.
And why don't you use off-policy algorithm then? RL off-policy?
Well, I think it's like off-policy RL for training this kind of model is not a given that they work, right? On paper, we have off-policy algorithms that work. In practice, they are much less data efficient. So it's always a trade-off, right? It's like, okay, you can use off-policy algorithm for this, but then it means you need to generate actually 10 times more data. So actually finding a good trade-off of policiness and policiness is a data efficiency issue.
But I thought that PPO was one of the least efficient, like for reinforcement learning, like PPO.
You mean sample efficiency?
Yeah.
Yeah, I'm not sure it's true. No. Yeah.
I mean, okay, because for subtype critic or whatever, you have replay buffer, but since you don't use that, then you, I guess.
Yeah, we do use replay buffers, but they need to be for stuff that is. So you can use, you have methods like Impala, for instance, right? where you do have a replay buffer, you have a correction for off policiness, but the correction for off policiness, even this correction doesn't hold for too long, right? If you are off policy by like 1,000 or 10,000 updates, I can guarantee you Impala doesn't work, right? So it's like off policy in the title, and it deals with some of the off policiness, but not like complete off policy.
But for a training that lasts 20 days, like is waiting like 5 minutes or 10 minutes or 20 minutes, does it really matter? Are you really...
What matters is the number of updates you do to the model. Right?
If the number of updates in between is not that high, it does it still matter that much or not?
Well, I think it's always the trade-offs between what you can do in terms of engineering and tricks, and the sample efficiency you want. If you don't care about wasting lots of compute, it's not a big issue. But I think if you do want to explore, and one of the problems is like you do want to explore also, right? You don't want to do just one job and cross your fingers and whatnot. So if you do want to explore, you care a lot about sampling efficiency. And I think like in general in RL, I think the unpolicy of policy issue is not solved. We still have a bunch of papers on that all the time. But in the case of LLMs, I think we also lack a lot of theoretical tools to understand what it means to change a policy, to do an update, and what it is to like if you strictly censure, this is an LLM is just something which has discrete actions. It has like 100,000 tokens and it generates 4,000 of them, 10,000 of them, right? So it's just like a discrete action space. But actually, I think we should see it more as like a continuous action space and have ways to measure off policiness of continuous action space under the kind of updates we do in when we do RL. Yeah. Yeah. Sorry, you had a question, Conrad?
Yeah. Let me see if I can reconstruct the exact. Well, like I sort of had a question with the off policiness. Like, what exactly is like? I guess there's a bit of an issue saying like token by token off policy, right?
Yeah.
That may not be exactly.
Yeah, exactly. The off policy applies to, I think, to the whole sequence, right? Mm-hmm. Token by token, there is very little change, but very little change when you have 100,000 things to choose from, and you propagate it over sequences of 4,000, 10,000 tokens or more, amounts to a lot of change from one version of the model to another version.
Yeah.
So that's why I think like we have no. I mean, as far as I know, maybe I ignore big part of the literature, but as far as I know, then we have very little theoretical tool to study what happens when we align those models, when we train them on policy data, or when we train them on other data. Yeah.
More questions? Yes? Okay.
Well, it's great, Thomas. Thank you, guys.
Thank you.